In this video, we're going to be going over problem 5.3 from our textbook. Now, this problem asks us to find the current IL through this 8 kilo ohm resistor. So, before we start doing calculations, we need to figure out what exactly we're asked for. So we know we want to find this current IL, and from Ohm's law we know that I is equal to V over R. So in this case, if we know the voltage across this resistor, and obviously we know its resistance, we can find the current IL. So let's say that we have a voltage at this node right here called V out. V out would also be the voltage across this resistor. So we can say that our IL is equal to V out over 8 kilo ohms. So now we've reduced our problem to finding this voltage V out, which happens to be at the output of our op-amp. Now in the introductory video to op-amps, we discussed ways to analyze op-amp circuits to find this output voltage. And the key thing in that video was we need to apply our ideal op-amp equations. So let's do that. Let's write them down first. We know our first equation is Vp is equal to Vn. So the voltage at this node, Vp, is going to be equal to the voltage Vn at this node. Similarly, we know In will be equal to 0 and Ip will also be equal to 0. So this current In is equal to 0 and this current Ip is equal to 0. So now that we've established these basic relations, we can start some analysis. Now we can see that the current right here in this part of the circuit is 0. The current going into the non-inverting input is 0. So where does this current go then? We have a 6-volt source. The current's going to go through the 10K resistor and then come down through the 5K resistor. So you should notice that this is just a voltage divider, and our voltage Vp will just be the voltage across this 5 kilo ohm resistor. So let's use our voltage divider to calculate the voltage Vp across this 5 kilo ohm resistor. So we know that our voltage Vp is going to be equal to our source, 6 volts, times our resistor, 5 kilo ohms, over the sum of the two resistors, 10 kilo ohms plus 5 kilo ohms, which equals 30 volts times kilo ohms over 15 kilo ohms. And kilo ohms will cancel, and we're just left with 2 volts. So now we know that our voltage Vp is equal to our voltage Vn is equal to 2 volts, and we can go ahead and write the voltage at this node right here is equal to 2 volts. Now we can look at the inverting input of the op-amp. We know the voltage over here is 2, and we know the current going into the input is 0. So let's use the fact that this current is 0 to establish another relation. Let's say we have some current I1 going through here, and we have another current in the feedback path called IF. Now we can do a KCL at this node because we have 3 branches and 3 currents. So our KCL will be what? We have a current I1 that's coming into the node. So we can write I1 is equal to, and this I1 splits up into 2 currents. It splits up into IN and it splits up into IF. So we have I1 is equal to IN plus IF. And we know from our ideal op-amp equation that IN has to equal 0. So now we're left with I1 is equal to IF. And let's go about calculating these now. So I1 is the current going through this 3 kilo ohm resistor, which would just be the voltage across this resistor divided by the resistance. So now we know the voltage across this resistor for the current going in this direction. We know that we have a 5 volt source here, but notice that this 5 volt source is not, like the regular polarities we're used to seeing, like this one. This one is flipped. And for this, we can think of it like this. We have our 5 volt source, which is like this. We can imagine it like a traditional source, except with a negative sign. We can say that this voltage is equal to a negative 5 volt source. So if we think of it like that, then we're just going to have negative 5 volts right here at this end. And we know that we have our voltage Vn on this end. So we can calculate I1 is equal to negative 5 minus Vn over 3 kilo ohms, which is equal to negative 5 minus 2 over 3 kilo ohms, which we can say is equal to negative 7 over 3 kilo ohms. So this is our I1. Now let's go about finding IF. Again, we apply the same concept. We know the voltage across this 6 kilo ohm resistor. We know that one end is going to be Vn, and we know one end is going to be V out. So we can say Vn minus V out over the resistance 6 kilo ohms is equal to IF. So let's plug in our numbers. We know Vn is equal to 2 volts, and we know that V out is what we're trying to find. So we'll just leave this as V out over 6 kilo ohms. And we established earlier that I1 is equal to IF. So let's set these equal to each other. Let's say that negative 7 over 3 kilo ohms is equal to 2 minus V out over 6 kilo ohms. And actually these should all be volts, 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 and volts. Okay? So now we just have to solve for V out. We'll multiply each side by 6 kilo ohms. So we have negative 7 volts times 6 kilo ohms over 3 kilo ohms is equal to 2 minus V out volts. Now kilo ohms and kilo ohms will cancel out, and we're left with negative 14 volts is equal to 2 minus V out volts. And solving for V out, we get V out is equal to 16 volts. Now we're almost done with the problem. There is one thing we should check. We mentioned in the introductory video about saturation, and saturation occurs when your output exceeds the range of your supply voltages. So in this case, our supplies are negative 20 and positive 20 volts. So if our output is less than negative 20 or greater than 20, our output would saturate to the supply voltage. But in this case, we're good. Our output is just 16 volts, which is well within the range of negative 20 to 20. So we don't have to worry about saturation. And now we just work on to the last step of the problem. IL is simply going to be our V out, which is 16 volts, over our resistance, which is 8 kilo ohms, which leaves us with 2 milliamps. So there it is. We've completed the problem, and we find that our IL is equal to 2 milliamps.